Homework 7, problem 1. Find the magnetic field directly above the center of the square loop, where the side length is L and the distance above that center is going to be D. And so this distance here, I guess, is going to be D. And show that as D is much, much greater than L, it reduces to the field for a dipole. To do this, we're going to, of course, use the Biot-Savart law. The Biot-Savart law, if we are going to write it down, is this. The magnetic field at some field point r vector is going to be equal to mu naught times the current that goes through the wire divided by 4 pi. And then we're going to integrate along the wire dl cross script r vector divided by script r vector cubed. And so this is the expression for the Biot-Savart law. Now there are going to be two tricks that we're going to use here. The first of which is, or not two tricks, there are two things that we need to do. The first of which is identify what the dl is and the script r vector is. Now our source point, this is going to be our r vector, and our r vector can easily be identified here. The r vector is simply d in the k hat direction. The source point is a little bit harder. That's going to be this chunk right here. So this will be our prime vector. And then the difference of these two, then of course, is the script r vector. So this is the script r vector. So writing this down, we can write down that our prime vector is, let's see, if we make this an x, y, z coordinate system, is that x, y, z? Yes, that's the correct right-hand rule. X, y, z coordinate system, then, and we set our origin at the center of the loop, then this r prime is going to be a over 2 times the I hat and plus whatever this y distance here. So we're going to call this distance here y, j hat. Using this too, of course, the script r vector is the difference between these. It is simply r vector minus r hat, which is minus a over 2 I hat minus y j hat plus d k hat. And so that's all that is. Now our dl vector can be identified. This is this little section right here. The dl vector is going to be dy in the j hat direction, right? In the positive y direction. So plugging all of that into our expression here, the next trick that we're going to use, right, is the fact that this thing is symmetric. We know that the magnetic field is going to point only in the positive z direction, and we're going to get an equal contribution from each of these little legs. So that leg will contribute the same as that leg, which will contribute the same as that leg, and so on around. There are 8 different legs around here, so we're going to multiply this by 8. So we're just going to write the bz as a function of d, so we're going to ignore the other components here. Is 8 times mu naught I over 4 pi. The 8 comes from there being 8 little parts of that. We're going to integrate from 0 to a over 2. dl is dy, so this will be dy, and then we're going to get j hat cross this script r vector. So this is minus a over 2 I hat minus y j hat plus d k hat. And we're only going to take the z component of that cross product, and this will be over script r to the magnitude of script r to the 3rd power, which can be written as a over 2 quantity squared plus d squared plus y squared whole thing to the 3/2 power. Now, to get the z component here, the only one that's going to contribute is the j cross I. J cross j is obviously 0, and j cross k is in the I hat direction. It's not in the k hat direction. So the j cross I gives us minus k hat. The minus is going to cancel with that minus there. And so the magnetic field now in the z direction, as we have it, is going to be, we're going to get the 2 from that a over 2 is going to go onto the bottom, so that will cancel with a 4 and the 8. So I'm just going to get mu naught I a over pi. Then I have integral 0 to a over 2 of dy over this thing on the bottom, exactly as we have it here. A over 2 quantity squared plus d squared plus y squared to the 3/2 power. Now this is one of those instances where it's best just to look these things up instead of trying to memorize the tricks of how to do all of the fancy manipulations, how to do all the fancy integrals. Instead of memorizing those tricks, it's best just to look this stuff up. Here's this integral done in Mathematica, exactly as I have it written here. And so simplifying this a little, I want to gather a over 2's all the time. So I'm going to factor out a 4, so I'm going to get a 1/2, because I'm going to factor out a 4 on the bottom and I have a 2 on top, so I can get a 1/2. And so this says that the z component of the magnetic field at D is going to give us mu naught I have an a on top, I already have an a, so that's a squared over 2 pi, and then I have to focus on what I have here. So this is 1 divided by the square root, just to make things easy. I'm going to say this is 2 a over 2 quantity squared plus d squared, and then this is simply a over 2 quantity squared plus d squared. And that is the expression for the magnetic field at that point. Now the second part of this was to confirm that this gave the correct expression for a dipole if you went up far enough. And so to do that, we have to look at what a dipole is. The dipole, or how to calculate the dipole for this loop. The dipole for this loop is the area of the loop times the oh, I had A everywhere. All these A's should be L, of course. I don't know why I did that. So this A here should be L. A should be L. This A is L. A is L. A is L. L. L squared, L. There we go. Okay, so we made all the A's L. Anyways, the magnetic dipole moment for a current loop is the current I times the area of the current loop, which in this case is just L squared, times the normal vector. The normal vector is in the z hat direction, or in the z direction, so that's k hat. Now, if I were to write down the magnetic field for a dipole, I can just look this up in the book. The magnetic field for a dipole is going to be, let's see, this is mu naught over 4 pi, and then 1 over the distance from the dipole to the object you're looking at. For us, this is going to just write this out. R squared for now, to the source point, or script R, I should say, from the source wherever the dipole is located to the point you're looking at. Script R. Then this is 3, and then we have m dot script R hat times script R hat minus m. And so this is just the expression for the magnetic field for the dipole. I looked it up in the book. It was equation 5.89 in version 4 of Griffiths, in Griffiths edition 4. For us, of course, the m is located. So for us, the m is located here at the origin. So r prime is just equal to 0. R is, of course, this dk hat, which means that script r is dk hat, right? And so writing all of this down, we get the magnetic field for this dipole is equal to mu naught over 4 pi 1 over d cubed, and then I have to evaluate this thing here. M is in the k hat direction, and this r is in the k hat direction. So m dot r is just going to give us m times this is r hat even, so r hat is k hat. So this is m dot k hat k hat. The k hats are going to cancel, I'm going to get a k hat left over. So this in itself for us is just m vector. So I have 3m vector minus m vector, so that's just 2 times magnetic dipole moment. So this is 2 I L squared times k hat. And that's it. So the final expression I have, right, is the magnetic dipole moment is mu naught over mu naught I L squared over 2 pi d cubed. And now we want to confirm that this expression gives this expression. Oh, this is a k hat here. And of course, I dropped the vectors when I did this initially, so there's still a k hat here and a k hat there. We want to confirm that this expression gives this expression. And we can immediately see that it does in the limit. Note that in the limit, as d is much, much greater than a, then an expression like the square root of 2a over 2 quantity squared plus d squared is just going to give d. And in that same limit, as d is much, much greater than a, L over 2 quantity squared plus d squared is going to give simply d squared. They'll be dominated by the d. This is so much bigger than this that we just ignore it. Same here. This is so much bigger than this that we just ignore it, and we're left over with essentially the square root of d squared, which is just d. So anyways, I'm going to have d and d squared. That's going to add to d cubed, and we find then, of course, that dz as a function of d is going to be mu naught I L squared over 2 pi d cubed k hat, which is exactly what we have. So we've confirmed that we get the correct expression in the limit that we are very far away from the loop. We get the expression for a dipole field, which is what we expected.